All right, so I have been told to start exactly at 4 o'clock. Our speaker today is Professor Eric Feigelson of Penn State University. Eric is an old friend. I think he and I go back over 20 years, in fact, and I don't feel that old, and I'm sure he doesn't feel older. Eric's also an old friend of here. He got his PhD here in 1980, working with Riccardo Giacconi, in fact, and from there moved on to that end of town at MIT, working with Claude Canizares, and from there to Penn State. The first place I ran into Eric's work was his work with Einstein. And he was among the first people to realize that young stars are also copious X-ray sources, and not foreground confusion or anything like that, but really astrophysically interesting sources in their own right. Did I catch everyone I'm supposed to? Okay. He is one of the leaders of the ACES science team. I believe you are the lead. We're the lead of the ACES science team. All right. But as part of that role with Penn State, organized the Chandra Orion Ultra Deep Project, also known as the COOP, which was about 2 weeks of Chandra staring at Orion, which gave rise to 22 papers, if I have the count correctly, and also 3 other similar type of programs looking either deep or wide at other star-forming regions. So really, it's a seminal kind of work with Chandra, which has really led to other works. And if you added all that together, it's probably 50 papers, or at least will be 50 papers by the time all that work is analyzed. Another main focus of Eric's work has been the development of astrostatistics, and that is what has brought Eric here for a school yesterday and more tomorrow. And if you'd like to learn about that, you can come by tomorrow in this room at about 9 o'clock, I think is when we're starting. And also, if you'd like to meet Eric a little more, some of us are going out to dinner afterwards, so hunt me down. But what Eric is here to talk to us about today is MYStIX. And this is not the river. It's a new way of looking at clustered star formation, and I will let Eric explain it.
Thank you very much, Scott. And it's a great pleasure to meet lots of old friends during the last couple days. I'd like to talk to you about star formation from a little bit of a different perspective than commonly done. There's many scholars here in star formation, some across the street in Concord Avenue, who often look at gas and dust. We're going to look at stars, meaning stars recently formed, and typically in the last couple of million years from gas and dust. And of course, along with stars come planets. I should say that this is really a group effort. It's concentrated at Penn State. Lisa Townsley and I sort of designed this program, this MYStIX program, a few years ago. It's an archive program. Michael Kuhn is a grad student who's finishing up. I'd like to highlight a lot of the work you're going to see is his. And also, he's looking for a job, and he's really good. Costa Getman is also working with us, and quite a number of other people at Penn State, students and others. Tim Naylor is a professor at Exeter, and that's the observing group. And now we're bringing in some theorists and multi-wavelength astronomers in the more analysis part. So I'd like to sort of motivate why we even want to talk that much about the star component of star formation, and then very quickly, go through technical aspects of the MYStIX project. The 7 completed papers are rather boring. They're catalogs and methodology, but they're needed in order to get some science. So I will then show you a little early results, which are essentially submitted, and a peek at what's coming up later soon. So to start off, let's look at the nearest massive star-forming region, the Orion Nebula region. It's very famous. There's roughly 3,000 stars down to the stellar limit in this picture here, a near-infrared picture. By the way, stars are actually forming in that yellow splotch up there. That's the OMC1 cloud core that has some protostars. But the other stars were formed a couple million years ago. And along with it, of course, are formed protoplanetary disks. So everyone now really cares about those disks because that's where the exoplanets come from. Now this picture is roughly, the one on the left, is roughly a parsec across. And that's about this big on this picture, and it's actually part of, as you can see, a elongated molecular filament that's several parsecs long. And that is actually buried in this white splotch here, part of something of 20, 30 parsecs in size of a giant molecular cloud that's very big and very splotchy and very complex, with tens of thousands of solar masses of gas that have made some stars in the past, are making some stars today, and will make others in the future. And so they're very complex in space and complex in time. And really, it's this complexity. We don't want to avoid the complexity of massive star-forming regions anymore. We want to really try to see if we can sort of understand it. So the Orion Nebula, for instance, is right here, and is estimated to be 1 or 2 million-year-old stars. But there's a cluster recently found by Alves and his colleagues that's older down here. There's an older one up there too, and then there's protostars in the middle. And this is all in a linear sequence that's several parsecs long. So it doesn't make stars in a consistent and simple way, but rather, I guess you might say episodes or in blobs. Maybe you'd call them subclusters. And then here's another picture of it. There's a Orion Nebula up there again, and this blue splotch is actually X-ray emitting gas found in this case with XMM satellite that is part of the winds from, in that case, probably just one O-star. And that's a whole nother aspect that is not well studied about the role not just of ultraviolet that causes the classical H2 region over here, but also the winds, which are now shocked and essentially become the hot interstellar medium. So Scott kindly mentioned this project that we did some time ago. This is just a small region now of the Orion Nebula. This is 2 weeks of data. And every single one of these X-ray stars is flaring. That was one of the biggest flares ever seen in any star ever right there. And from the entire initial mass function, except for O stars that make stars X-rays in other ways. And the point is that every young star emits a lot of X-rays. So we started with this X-ray perspective. And we're X-ray Chandra astronomers, we're a Chandra instrument team, and so it's natural we think of X-rays. But this talk is not really about the X-rays. It's using Chandra as a finder telescope to try to address some more astrophysical questions about high-mass star-forming regions. So what we realized is that because of that image that found every known star almost in the Orion Nebula, where the catalog of stars was already perfectly known, it's the only cluster where it's perfectly known. The initial mass function of stars is defined in the Orion Nebula cluster. So we might use it just as a telescope to try to find young stars in less well-known regions. And it ends up that there are actually rather poor catalogs in many of these regions, and X-rays are rather good. So first of all, it actually captures all phases of the young stars. Class 1 means a protostar. Class 2 is called a classical T-Tauri star. Class 3 is called a disk-free pre-main sequence star. It grabs all of them. It's particularly important for capturing the class 3s because those are hard to find by infrared astronomy. Their disks are gone. It actually penetrates surprisingly deeply into clouds. It's not restricted like optical astronomy to what's in front. And also, it doesn't have much contamination of nebular emission, but it has some of this diffuse plasma from the OB winds, which is a new component of what might be called OB feedback. And the O stars feed back and eventually destroy the clouds around them. So it's really interesting and complex, and X-rays give a new view of it. Now, the telescope that we have is wonderful. It has sub-arc second resolution on axis. It's called Chandra. It's 17 arc minutes in size. And it ends up that's not a very good size for the nearest regions, because the nearest regions, if you want to do mesoscale work, are degrees across. So we like to work a little further out than Orion. We start at Orion molecular cloud, and we go out to molecular clouds typically around 2 kiloparsecs. And these are, as you'll see in a few minutes, you'll see the list of them. They sort of have famous names from the 1800s, like the Lagoon Nebula and things like that. And we often do, it's still not big enough a telescope, and so we do MYStIX to get the larger scales. And that's what the MYStIX project's about. We simply mined the Chandra archive, which is very rich now, and then we went to near-infrared and mid-infrared astronomy, and we mined those data sets or took new data in order to get complementary information. So we worked for 3 years on data analysis. It's now over. We're now writing papers. And here again is the team. And here's some of the theorists. And these last two you won't recognize. They're actually statisticians. You're going to hear brief references to some, let's call it, somewhat sophisticated mathematics or statistics methods to try to help us through the mess of dealing with these very complex regions. So why do we bother? What are some of the questions? Well, over the last decade or so, we have great theorists like Dr. Elmgreen and Dr. McKee, one arguing that clusters form just in one crossing time. You make 1,000 stars basically overnight. And another says, no, you sort of simmer them and you brew them and you make them slowly. And there was no consensus on that for many, many years. There still isn't a consensus. Another is, well, you don't even form a cluster at all, 1,000. What you do is you form 100 or 50 or 30 over there, and they consolidate. You get subclusters that sort of merge. And that's been proposed for years, and we don't know if it's true, although there's a lot of evidence increasing of this sort of filamentary flows and turbulence in the clouds, but we're not really sure how that affects rich cluster formation. Once you form a cluster, how does it evolve? For instance, the gas has to be escaped from the O-star H2 region. Does it just expand and dissolve, or does it concentrate in the middle? Something called mass segregation, where all the O-stars from the middle, or what's going on? And then, what is the nature of the feedback? The feedback is really a big, complicated mess. Feedback is due to several different causes, and it maybe have trivial effects or very, very strong effects. For instance, it's possible that on the edges of H2 regions where we see sort of pillars and bright rim clouds, it could be that there's not much triggering of star formation. It could be most stars are formed in triggered edges of H2 regions. We really don't know until we count them well, and it's rather hard to do so. And what are the H2 regions filled with? Harvard was famous under Doctors Menzel and Goldberg in the middle part of the 20th century for saying that H2 region physics is understood. It's all 10 to the 4 degrees as a uniform sphere of gas. That is now completely wrong. Okay, the sphere is filled with 10 to the 7 degree gas, and the Stromgren sphere is a complicated shell on the edges. And then planets are ubiquitous. But there's a theory that if a protoplanet gets close to an O-star, the O-star will evaporate the disk and maybe prohibit the planets from forming. We're not sure how important that is. Okay, so when it comes to how do clusters form, this is just one theorist's idea, but I like this movie. It came out a few years ago by Matthew Bade at Exeter. This was a turbulent, sort of massive cloud, and gravity is involved. In this case, it is stirring the little white dots are the stars forming, and you can see, there's a subcluster forming, and here are two subclusters, and watch them. They just merge to a bigger one, and that one's falling into, the gravity's pulling them in, and these filaments are streaming in. In fact, those of you who do large-scale structure of galaxy formation, I mean, you can just change the scale by a lot, and it looks like a galaxy is forming with a halo, dark matter halo. And now they're consolidating and flowing. And look, nobody knows if this is right. Okay. But it's really beautiful. Okay. And the goal of observers is to tell which theorists are right and which ones are wrong, and to guide theory. So thank you, theorists. It's very important to have that. But fundamentally, we don't have the elementary astronomy to test this. We don't, except for the Orion Nebula Cluster, we don't even have a census of stars in very famous rich clusters that have been known for 200 years because of the nebula or the cluster. And the reason is There's molecular clouds obscuring it, or in front of it, or right around it. There's nebular emission, like alpha and BRAC and gamma, and all sorts of horrible things that optical and infrared astronomers hate. Okay? There's crowding, particularly if you happen to have your cluster superposed on the galactic center, which some of the important ones are. And then above all, when you get to 2 kiloparsecs, you have 2 kilothousand parsecs worth of normal, uninteresting field stars in front. And if you're a good infrared astronomer, you see 8 kiloparsecs of stars behind, and you can't even decide which ones of the stars you see are, in fact, the young stars. You know, it's just a very messy environment that has prevented good observational progress to help and guide the theory and the issues. So we take Chandra, and we take a fairly modest ground-based telescope. It's UCURT, often from the UKID survey. And we take a Spitzer IRAC. And those of you involved in the IRAC project, I just want you to know you have a magnificent telescope, too. It's just fabulous. So here's our sample. Orion Nebula. Imagine I was John Herschel in the salons of Victorian London and telling the stories of the Eagle and Carina and Trifid nebulae that I found in the southern hemisphere. Okay, I mean that's where the heritage is of these objects. If it wasn't John Herschel, it was his father, William Herschel. Okay, so all these have been known for forever. Okay, and yet we don't have catalogs in most cases, good catalogs. Typical distances, 1.5 to 2 kiloparsecs. Typical galactic latitudes, 0. They're right in the plane. Okay, that's where star formation occurs in our galaxy, of course. So this is then the sample for which Chandra saw it, and we got UKIDS and Spitzer IRAC data. So now I'm going to, thank you. That was the introduction to why and the motivation for MYStIX. So now I'm going to whiz through 7 technical papers that represent about 20 man-years of work. It was just agonizing. And I'm not going to do a good job. Okay, they're all in AppJ supplements if you want, just a couple months ago, a few weeks ago. So one thing with Chandra is that they're very crowded and they're very messy, and also Chandra has a really bad point spread function, vignetting problem. It's built into X-ray optics. And we have these mosaics that miss point. It's a very messy environment. Fortunately, over years, the ACES team has developed software called ACES Extract and other strategies for doing a really good job for this particular problem. Finding faint sources in variable backgrounds due to the overlaps or even due to diffuse emission, often overlapping point spread functions in the middle because they're crowded, and we actually get really nice X-ray catalogs. We're able to get catalogs with sources with, let's say, 4 photons in a week of observation. I mean, Chandra has no background. It's just astonishing. So the sensitivity is linear with exposure time. Name me another telescope that does that. Okay, so it's really good. And then you come up with, for instance, my color schemes will change. In this case, the MYStIX probable cluster members are in black. So you can see this is now X-ray flux. This is X-ray color. Median energy is a color index. Essentially, median energy means this is heavily absorbed. These are 100, 200 magnitude absorbed, and these are unabsorbed. Okay, this happens to be the Lagoon Nebula, okay? And you can see that it's fairly lightly absorbed. And we find a lot of black dots. Those are the stars. And later on, it took a while to get there. The blues and the greens are the X-ray sources that we don't believe are stars. They're probably quasars and some foreground stars. So we have to go through a complicated process to classify the blacks from the other. But the MYStIX probable cluster members is the goal of this part of the project. Here's some UCURT data. The black, again, are the ones that we eventually find are MPCMs, the members of the clouds. This is DR21. Most of you haven't heard of it. Lagoon, Rosette Nebula, Eagle Nebula. So let's take a look at Eagle up there. Do you see how many red dots there are there? Those are uninteresting field stars. They're just gobs of them. Now, fortunately, in the case of Eagle, they're nicely segregated in a near-infrared color magnitude diagram from the MPCMs. So how do we achieve that? How do we pull them out? Well, you can't do it from near-infrared alone. You can't even do it from Spitzer alone. What we're doing is we're combining Chandra and JHK and Spitzer together and doing, frankly, statistical magic that may or may not be right, okay? And notice we use the word MYStIX. Probable cluster members as probabilistic elements to our calculations, and to pull out the black things from the red things. And sometimes look at DR21. They're completely superposed on some diagrams, and you would never be able to find them that way. Here's some Spitzer data. This shows you that at 8 microns in particular, there's a lot of diffuse emission. It's very hard to see. You understand, the Spitzer team makes press releases on the gorgeous pictures of the heated dust. And we hate those press releases because how could you find a star in that beautiful, bright, heated dust? So at 3.6 microns, it's a little better, but it's even nasty there sometimes. And so we changed your pipeline to be more efficient in finding faint stars in these complicated environments. And we changed the UKIDS pipeline. We changed every pipeline to sort of try to adapt to our difficult problems in our single wavelength catalogs, and then we combine the catalogs. So here's an example of this, the single waveband catalog. Again, this time it is red and greens together are the MPCMs. The greens are the infrared excess disky ones, although some of them don't look excess in some diagrams because our criteria are sort of non-standard. And the greens are the disk-free X-ray selected MPCMs, and the black dots, which are often extremely populous, are the uninteresting field stars, and probably some galaxies. So again, we have a very tricky extraction problem, and you're looking at the result of that extraction process, we didn't derive those colors from that diagram alone. So one of the things is to just match. This is a well-known problem. You have an X-ray source, you have a near-infrared source, you have a mid-infrared source, and you just take RA and DEC and in an arcsecond, they're fine. You use what's called proximity matching, but as a criterion. But listen to this. Your X-ray source has an error circle. And then you're looking in the galactic plane. You have a shallow infrared image. Well, you either find a bright infrared star on it or you don't. Then you get better and better and better and better and better to get the embedded ones and the fainter ones, the M stars. And you're more chance you'll find it, but there's more chance you get a field star. So the better your infrared data is, the worse your matching is. And that insight came from Tim Naylor, and he devised an improved Bayesian statistical algorithm based on another British study some time ago that said we would have just proximity taken every single one of these symbols here and said that was, by virtue of their close distance from the X-ray star, that's the right closest proximity source. But the colored ones are the ones we chose, and the ones that are a little further away and a little fainter, like 16th magnitude instead of 14th magnitude for this particular cluster, we found that there was a brighter but more distant member that we think is the more likely member. And are we right? Probably. That's what mystical probable member means. We're probably right. So we're not even sure we know how to match our stars in the galactic plane. We're probably doing a good job, okay? So when we get, and this is now for any Iraq people in the audience, here is the results of a very sophisticated work by Matthew Povich, who's a descendant of Ed Churchwell and the Glimpse team when he was a student. He was an NSF postdoc with us for a few years, and he worked very hard to do this. These are the infrared excess MPCMs associated, superposed on a Spitzer image, segregated by protostars in red and T-Tauri stars in yellow. This does not have any X-ray sources, this particular picture. And oh, look at that little clump of protostars. Isn't that cute? Okay? But how did he get this? Okay? It was absolutely amazing. If you just use a standard polygon in a color diagram. This happens to be one of the worst ones. It's the Trifid Nebula. All of those dots are infrared excess. And I'm sorry, there aren't that many protostars made in this region by 2 orders of magnitude. So he had to throw most of them away. So he had all sorts of complicated, difficult decision rules to get rid of disk-free stars and PAH knots and dusty galaxies and bad matches and active galaxies. And he just had took very conservative criteria that he was really sure that was an EGN disk. He used Robitaille SED fitting. For those of you who are professionals, you'll recognize those phrases. And he ended up with clean but small samples for that purpose. And finally, my colleague Patrick Bruce uses a naive Bayes classifier as a statistical tool. It's actually rather simple. But let me tell you what it does. It says, okay, we have infrared spectral energy saying, oh, I think there's an excess. And we have some infrared magnitudes, but we have OB spectra, we have X-ray flare sometimes, and we have X-ray absorption sometimes, and J magnitudes of certain distributions. How do we combine, this big bushel of apples and papayas and pineapples and fruits into a nice simple statement as which stars are members? So for heterogeneous data, sometimes even classificatory data, not even real numbers, this naive Bayes classifier is very good if you can fully characterize all of the contaminants in all of the variables. So we simulate the heck out of the foreground star population, the background star population, and the AGN population. This is only done in X-rays. Most of the classifying is done in X-rays. So here's an example. This is the absorption distribution for a certain cluster that's not really absorbed. For the red one is the T Tauri stars. That's expected. And then this one is for the background stars, and that is the distribution for the quasars, and that's the distribution for foreground stars. And the point is that for this particular variable, and there's 8 of them, is a moderately good discrimination from background stars and quasars, and not so good with respect to foreground stars from this particular variable. So we would put this probability into the model, multiply by other probabilities, and come out with the MYStIX probable cluster member sample. And here are 4 of the roughly 20 regions for which we have completed this work. Rosette, Lagoon, Messier 17, also known as the Omega Nebula, and NGC 2264. Yes, NGC 2264. It's blurry, but that's what it is. And in this case, every single dot you're looking at is an MPCM. This is our final result. The yellow dots represent those that were found with X-ray selection. You can see in M17, most of them were X-ray selected. And the red ones were found with infrared selection, infrared excess selection. You can see in NGC 2264, most of them. And down here were infrared, but up there was mostly X-rays. Many of the dots, you can't see them here, have both a yellow and a red a symbol at the same time. They were found both ways. Up there in Lagoon, you can see some blue dots, cyan, I guess, and those are OB stars. And so what we're doing is we're saying, look, if you're just an infrared excess astronomer, you capture some of these. If you're just an X-ray astronomer, you capture some others. There's actually Venn diagrams of the overlaps of these. But only when you combine infrared and X-ray together can you do a good job in finding them all. No, I don't mean them all. I mean finding a better and richer sample. It's still only a small fraction of the true initial mass functions. Even when we see a few thousand members, it's only 10% of the true IMF of these regions. So that, ladies and gentlemen, is my summary of what we spent 3 years doing. And there was a real risk, and there still is a risk, that what we're doing is, garbage, okay? Because we just have too many contaminants, and we can't clean our samples enough. but it's also possible that we did a great job. So we did some validation, particularly on this particular region here. Aside from the Orion Nebula, NGC 2264 is the one that's been studied, the stellar population has been studied well since the 1950s. And there's actually well-known catalogs of H alphas and optical, it's not absorbed, optical works. And we found that basically we would recover roughly 80% of an H alpha catalog, and roughly 80% of an infrared catalog, and roughly 80% of a variable star catalog, which we didn't even use in our criteria. And then we would add it up and we'd find out, well, we had another 300 stars that nobody had found before at all. And so we're bigger than all the others. So are we reliable? Generally, it looks like it's generally reliable. Are there mistakes? Oh, without a doubt. They're mostly foreground background stars that we mistaken, that look too much like a T-Tauri star and fooled us, fooled our algorithms. But we believe this, we know this is the richest samples of star catalogs for these regions, and we believe it's reasonably reliable, and we're willing to do science on it and try to reach scientific conclusions. But be aware that the foundations have to be thought about, and they may not be perfect. What we would love, by the way, is K-band spectroscopy of 31,000 stars. Okay, anybody? Okay, that would be a confirmatory a step forward. Also, you get radial velocities out of it. This is important. Okay, these are great catalogs for future spectroscopic work. Okay, let's get to some science. Let's assume everything's great. Assume those catalogs are fantastic. What do we learn? So we're going to talk first about morphology and dynamics, and then I'm going to talk about age. And they're related to each other. Okay, now, again, I don't know if you remember, but I mentioned the Chandra fields have these sort of bowl-shaped sensitivities because of the optics. And what we did here is we flattened the X-ray fields, and that meant we threw away like 70% of our sources, or 80% of our sources. So from 31,000, we threw most of them away, and we made a map. And here's a map of the MPCMs. So it's not perfect. There's some regions that are saturated from PAH lines that we don't have good infrared accesses. There's some problems, but roughly speaking, these are the best comparative maps of where the stars are in high-mass star-forming regions ever produced. But this is a lousy map. This was Michael Kuhn's 2014 A paper, because this is actually sort of observed stars. And this region is about 3 times closer than this one, and whatever distance squared. You know, there's a huge sensitivity difference just by distance and exposures are different. So we have to normalize them to something more real. So we corrected for the X-ray flux sensitivities, and we kept in all the infrared and OB stars, and we showed the maps again. This is Michael Kuhn's paper 2014b. And this is the right map to look at. This is the first view that is honest. Look at the units. Intrinsic surface density of stars per square parsec. Now, it's still not, quote, no, excuse me, this one is. This one has been integrated down to the stellar limit. We've extrapolated, we've rescaled the observed assuming everyone has the same X-ray luminosity function as the Orion Nebula cluster. And there's some reason to believe that's a good assumption. Notice we've also rescaled them so that they live on the same parsec scale. So those of you at the Chandra Center, oh, look how teeny-weeny some of your fields are. Look how big some of your fields are here. Well, that's because the objects are at different distances. And when you scale them to parsecs, you're not covering the same regions at all. So this is, again, the best honest view in both true spatial units and true surface density units of where the stars are in these numbers, about 17 of them here, I think, star-forming regions. Okay, I personally think this is an observational accomplishment, never before attempted. It may have been done for one or another region, but never in a comparative way that allows, treated in the same way to allow comparative work. Okay, so one thing to do is to then sort of asked about the morphology, and we can just eyeball them. But Michael Kuhn is actually a good young statistician, and I'm an older statistician. And we met Adrian Baddeley, who's a brilliant statistician. He's actually a real statistician. And so I sent Mike down to Australia to work with Baddeley for a few weeks. And they did Mike did a maximum likelihood finite mixture model with isothermal ellipsoids as the parametric model, using the Akayiki information criterion for model selection, and minimizing the residuals, minimizing the maximum residuals on the residual map. And that sentence was made for almost nobody in this room. Okay, if you're interested in statistical methodology, it's a spatial maximum likelihood calculation. And from that calculation, he gets these black ellipses. So the black ellipses were calculated using pure math from the individual star locations, nothing else, just RA and DEC. And we have an ellipse there because the likelihood required a new ellipse there. We had them there because they required. We don't have extra ellipses because the likelihood wouldn't allow them. We have just the right number of ellipses. That's what Akayiki information criterion does for you. Does it do a great job? I don't know. It's not perfect. Certainly in Carina, I don't believe that ellipse exists. It just means there's a distributed population. Okay? But if you look at it on just a regular contour map, oops, those of you who took my class yesterday, that's a kernel density estimator, okay? A normal kernel density estimator, that's the smooth color map. And look how nice the method is. Do you see that one called RCW36 up there? Do you see it has two little tiny ellipses inside of a big ellipse? That method can do that. We call those core halo. And we went and spoke to our theorists, and they said, you found core halo? That's nothing we've ever predicted. That's actually theoretically interesting, that one up there. Then this one here is a simple isothermal ellipsoid. Well, that's astrophysics 101. That's what we sort of expect to cluster Orion Nebula. Lynn Hillenbrand and Lee Hartman said that about Orion Nebula 20 years ago, so we expected them all to look like that. But some of them are basically, so many ellipses, it's just ridiculous to believe they're real. Let's just call them clumpy. Complex. So here's a diagram of all 17 of them on a true parsec scale of clumpy structures, core halo structures, chain linear structures, and simple structures. By the way, if we only had a much bigger Chandra, we would have found, as Alves showed earlier in my introduction, that probably Orion doesn't, which seems to be simple, really belongs in the chain. It's really a linear structure, if we only had a big enough picture. Okay, thank you, Mr. Kuhn. You've told us something about morphology. What can we learn from your ellipsoidal fits? Well, he has for each one of them. He knows the central star density in stars per square parsec. He even knows it in stars per cubic parsec. Now that's an interesting number. That's physics. You can actually, go to Binney and Tremaine and use a formula and actually calculate things. So here is an inferred, each symbol here is one of his ellipses. And this axis here is the density in solar masses per cubic parsec. So it's real physical units. And this one is the core radius. Isothermal spheres have core radii. The core radius, 1/10 of a parsec to a parsec. And of course, you actually see stars usually out to several core radii, so they often look bigger than this. And there's this incredible correlation. Well, ladies and gentlemen, it's actually not that unexpected. But in a few minutes, I'm going to tell you that we have evidence that the ones over here are younger and the ones over here are older. And by combining the morphology with our new age estimate coming up in 2 minutes, we actually get an insight. It supports a model that clusters are born, younger means they're born, very high density and very small. Not necessarily very rich, I don't have richness on here. Most of these are not very rich. They haven't merged yet. And as they evolve, older, they get bigger and less dense. They expand. Well, guess what? That's one of the things the theorists always expected, that clusters expand. In fact, many clusters should expand and just evaporate. And the reason they expand is that they're born in molecular gas, and the star formation efficiency, as Charlie Latto once derived many years ago, is always less than 50%. And so most of the gravitational potential is gas. And when the gas is blown away by the O star, the gravitational potential is lower, and it just has to expand by just virial theorem. The mass goes down, and it has to grow. So this expansion is actually expected, and it actually has been reported observationally by Suzanne Falsner. And those papers by Falsner have been sort of, I'm not sure the word is ignored, but at least not widely respected as a genuine observational result. We support it entirely. So we are supporting a previous observer in direct evidence for clusters forming at high density and small sizes, and possibly uniformly so. Why aren't there any younger ones that are sort of over here? We could have found them. Okay, I don't think we would miss them, but they don't seem to be there. So this seems to be a very dramatic result. Maybe not completely new, but very dramatic nonetheless. Here is a multivariate plot. This is from 2014b, which is still won't see the light of day quite immediately. The result I just showed you is this correlation here. That's a log radius plot. This is small, and this is a youth age. This is young, and that's the correlation I showed you. This is the one with the, this is the correlation underlying the younger, older annotation. This is the correlation I showed you between radius and density. You understand, of course, density has radius cubed inside of it. So it's not a big surprise that there's a relationship here. But the issue is that it's really tight, and that it satisfies this. And then there are other relationships that are of interest too. Here's one. The ones that are most heavily absorbed are the youngest, which of course is also what we would expect. So we have some nice morphology, and we're leading from morphology to physical units and trying to do astrophysics. Okay, Michael Kuhn's dissertation. In addition to being in the mines for a couple of years doing data analysis. Okay, let me take you to Costa Getman. Costa is one of our scholars in our department for many years. He's done lots of good work on young stellar systems, stellar populations. And he put together one of these things that just sort of afterwards say, well, gee, why didn't I think of that 10 years ago? You know, it seems like obvious, and it was not obvious it would work so well, but it seems to be working fine. The issue is, if you have a single star or a small subcluster of stars like those ellipses, how do you know how old it is? Well, if you knew exactly the distance and exactly good photometry, you could put it on the HR diagram, read off a Hayashi track, evolutionary track, and you can read off the age. But we don't have those distances really good enough. So we need essentially equivalent to a distance estimator. We need something to hold on to. So this was done mostly in the optical for nearby regions using the Hertzl and Russell diagram. And every single case they've ever done it, there's always been an age spread in the clusters, in the HR diagrams. And there's been a huge controversy for years over whether those age spreads are real or are due to mistakes. Oh, let's not call them mistakes. Due to complexities in the system, okay? And so this is just a real hassle to the whole community. Basically, we don't have reliable ages. So what Costa realized is that both I published the first one in 1993 with Rosat, and others. This is the group by Manuel Gödel and his colleagues with the XMM ZEST survey of Taurus, found that there is a very strong correlation between X-ray luminosity and the mass of the pre-main sequence star. This correlation doesn't exist on the main sequence, only exists on the pre-main sequence. The reason for this correlation is, I don't know. But Henrietta Leavitt didn't understand the Cepheid periodic luminosity relationship. Wasn't understood to the 1960s. Okay? Arthur Eddington didn't understand L goes with M to the 3.5 relationship on the main sequence. It was just empirical. So I stand in good company. Here's an empirical relationship over 4 orders of magnitude of X-ray luminosity. I measure my X-ray luminosity and I read down and derive a mass. You believe me? It's as good as them. Okay? They're famous. Okay? So that's what he did. He reads off, he reads down, he gets a mass estimate. So once he has a mass estimate, he doesn't need a distance. He can read off, just take the J magnitudes. He does a lot of reddening corrections as needed. And he can read off the evolutionary track diagrams and read off and derive the age of the system. He does have to assume a distance. I shouldn't have said that the distance is unknown. He has to assume a distance. Each one of these regions has a distance estimate that might be good or might be bad. And is Dr. Reed in the audience? Okay, you and your colleagues who use VLBI, occasionally you've given us incredibly precise distances that are often show the old values are bad. But sometimes, often, you haven't succeeded yet in finding the right radio source to do it on. So I encourage you to work on this topic so that particularly Mark, that's your next proposal to reveal it. Okay, thank you. Yeah. Okay, so he has this sort of X-ray infrared derived age estimate, and it's really appropriate for MYStIX because we don't have optical data, and we have X-ray and infrared data. So it's very closely attuned to ours. And then he applied it to Michael Kuhn's. He's supervising Michael Kuhn's thesis. We're all friends. We're all working together to his superclusters, so to his subclusters. And he uses very strict criteria. It has to be good X-ray data and it has to be really good infrared data. So he throws away, from 31,000 stars, he throws away all but 5,000 and only deals with really good stars and then takes the median value, which is a stable estimate of the middle of a subcluster value. And this is a typical result. He finds the L subcluster of NGC 6334, it happens to be in the upper left of the image, which is right in the middle of a very massive molecular cloud, to be quite young, roughly 500,000 years. And he found the B supercluster, which you can see over there, is actually not on a molecular cloud. It actually seems to live in front of a molecular cloud, and it seems to be 2.5 million years old. And there's a lot of purple, magenta stars. Those are the unclustered ones, and they're always older when you take a median of their ages. And he very, very consistently finds age that the different subclusters at different spatial locations, coherent clumps of stars, typically have different ages. And typically the unclustered stars are even older. And sometimes it goes blub, 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 blub. The age goes in a straight line, and sometimes it doesn't. We already saw off my introduction, the Orion Nebula. It went 4 million years, 0.1, 2, 4. It wasn't consistent. So I didn't say they're all a simple age gradient, but we do see age differences. Well, what did we learn from this? First, we learned in 17 different regions that the age spreads are real. And then we learned that the age spreads are spatial. This clump formed there at this time, and that clump formed there at that time. Some of them are old and revealed, have no molecular material. Some are deeply embedded, and some are in between. In fact, everything he finds, he looks at the molecular maps or the dust maps from Herschel or from Spitzer, and it seems to be reasonable. The older ones are far away from the cloud cores, and the younger ones are inside. So the age spreads look real over sufficiently large regions, and it seems to make sense with respect to what we would expect from star formation from what we know. So this is a major result, ladies and gentlemen. Even if you think it's already known, it ends up it's never been demonstrated so clearly, particularly that we have 17 of these pictures, not just one of them. So, excuse me, there are people in this room, is Marcello here? Okay, that you've done this for 1 or 2 regions, and we've redone yours and done 17 others, okay? So we Marcello, your work is right, okay? Okay. Sorry, Mario. Okay. Now here's a new result, and this one was surprising. And if you're a star formation theorist, let's say people like Phil and Charlie, okay, I'd like you to listen now, okay? This one is.
Speak for yourself.
This is why I come back every once in a while. Yeah. Okay. This is a curiosity. This is within a single cluster. This is just one of Michael Kuhn's ellipses. It happens to be nearby and rich, which is why we were able to do this one separately. You can see we threw away most of the stars. We have a relatively small sample because of very strong quality control for the age calculation. And we find this from 0.1 million years, that means like protostars, okay, up to 1.5 million years. And it is a completely coherent spatial pattern where the core is younger than the outer parts of the cluster. And this is not expected. Because if I was, James Jeans or something, in the classical model of I have an isothermal cloud that's dense in the middle, my Jeans collapse time is shorter in the middle, and I should make my stars in the middle first and make my stars later and later as I go out. And then a couple million years ago, click, and I take a picture of it, the halo would be younger than the core. The core is younger than the halo. It's backwards. So we announced this at a meeting on the Orion Nebula Cluster a few weeks ago in Space Telescope Institute, and it was right after a lovely young theorist gave a talk on the reasonable theory that gave the other prediction, and we said, we're sorry you're wrong. I mean, at least for this case you are. Okay, so this was a big surprise. And it's not impossible to arrange for theory to do this, but it's very interesting to do this. Think of Matthew Bates' movie. Think of making some stars in the filaments that are then stream inwards and dynamically interact and spew out stars. Maybe those are older stars. And maybe continues to make stars in the middle. That's the kind of more complex model implied by this. So Matthew's interested, I think. And I hope other theorists are interested as well. So we believe that cluster formation is now finally a little bit of empirical input is coming in to the theory to help guide us to understand what's going on. Oh, that's fun. Did you see that? Anybody? There we go. It's rather hot. Let's see if I can recover here. Okay, let's try here. So in summary from Costa-Getman studies, we have essentially expected larger scale age gradients and age differences, such that the youngest subclusters tend to be embedded inside of molecular cores. The revealed subclusters, often very rich NGC clusters, tend to be revealed. And then there's a dispersed population that tends to be oldest. And this seems to be very consistent across the regions. And then there's, at least in 2 cases so far, we have an unexpected smaller scale age gradient that the cluster cores are younger and has strong implications for how star clusters should form and some sort of feeding of gas into the cluster core or something that operates in a similar fashion. My personal opinion is that's the hottest result we've had so far. I don't know what's going on. When Microsoft wants me to tell me to do something, I'm not very happy. Okay, now I'm going to show you things I'm a little worried to show you. I wouldn't mind showing you, but I heard this is being webcast. So it's not that I don't believe what I'm going to show you. It's that it's really not really finished yet. These are results off the computers of the graduate students from last week. Okay, so I don't promise you this is all right. But it is also, for those of you who saw me yesterday and maybe tomorrow, examples of some statistical techniques that are not commonly used in astronomy, and we can see that maybe they can be valuable for scientific work. So this is not a very complete presentation. It's like one slide per topic, maybe two. So this is a method called kriging that's used very extensively by geologists, particularly by petroleum engineers who look for petroleum by drilling wells in irregular spaces and mapping layers of shale and trying to make money for Exxon. And they use this method for 50 years. It's a least squares method. It's a maximum likelihood method. It's a way of making a least squares map of a mark variable, and I mean the separate variable from the actual samples, and then also the variance of that. How reliable is it? Some of you may have heard of this method in a very different language. It's related to what's nicknamed Gaussian processes, and Gaussian processes is now rather fashionable in certain time series problems and other problems. And basically it's the same as kriging. Jogesh Babu, my colleague, tells me mathematically that they're very closely related. And so essentially this might be called Gaussian processes spatial modeling. So here we go. Here's the eagle. Here's a bunch of red and yellow things. That means infrared and X-ray things. But I've pouched out this weird white thing. Those are the places where I don't believe the infrared data because there's too much PAH diffuse emission, which is, in this particular case, half the field. So I'm left without that. But I mapped it anyways. Excuse me. Alex Reichert, the grad student, mapped it anyways. He did it all. He does it all in R. Those of you who take the class. Okay? And it's a few lines of R, very fast. Okay, very easy. No. And basically what you find out is that the main cluster, what little bit that you know, and it's known reliably, blue here means reliable, it seems to have a low disk fraction, that it's basically a revealed cluster without many disks. But that spot up there, with medium reliability, has high disk fraction. Instead of, subtract one from this, instead of 20% disk fraction, it looks like about 80% disk fraction. So we're trying to do some disk fraction mapping, which will then be compared with our age estimates and our morphology discussions, and to try to see how protoplanetary disks fit into the story of cluster ages and cluster structures. We're not expecting big surprises. We're expecting that clusters that live inside of molecular cloud cores, which Costa-Getman's age JX method says are young, we expect those to have high disk fractions. And so far, we haven't had any surprises. So this is going to be a nice effort. It's just never been done before. No one's used kriging for anything in astronomy. Okay, so then Alex Reichert, the student, then is able to use the same sort of technology and ask a different question. In this particular region, this is Eagle Nebula. It has 32 known OB stars. So essentially, I think the astronomer would say he stacked the 32 OB stars right on top of each other and spatially looked around them, now stacked in parsec units, and said, which of the stars around them have disks and which don't? The reason is that from Hubble Space Telescope pictures of the Orion Nebula, we think that O stars evaporate disks. They're called proplyds, these streams of things pouring out of the disks. And this actually does support it. This is a very important picture. I should have written preliminary because I don't want this reported yet. But if this is true, this is the first time that anyone has given evidence outside of the Orion Nebula that the distance distribution of disky stars in black has generally further distance away from OB stars than the ones without stars. It supports the photoevaporation and ablation of disks by OB stars outside of the Orion Nebula. Okay? The theorists, for instance, David Hollenbach, distinguished theorist from Berkeley, had a whole theory that this should happen. And if we didn't see this, I mean, he has to come out of retirement. I mean, you know, but he doesn't. He's happy. I mean, he should be happy. He doesn't know about this yet. Nobody but you know about it. You're the first person to see this graph. In fact, until last week, I was the second person to see this graph. Okay, so no one's seen this graph. Okay, it's brand new. I hope we're right. Another is to find all the OB stars. Now, we're taking OB stars from the published catalogs, generally done in the 1980s and 70s by optical astronomers looking at blue stars. But what if you have an embedded O star? Well, it won't be blue. It'll just be luminous. So we looked at the high brightness K star candidates, counterparts to the MPCM sources, and doing some magic that my students Heather Busk and Matthew Povich did, basically said these are candidate OB stars. We need spectroscopy to show them. They're shown in yellow, and the magenta shows the one that were previously known. And sometimes, it's funny, sometimes it looks almost like the same object there. But anyways, it must be it's a binary. And here's the result. For those on top, we found no new ones and 0% increase. Those on the bottom, we found some new ones, and sometimes we doubled the number of OB stars. And in my personal opinion, this is profoundly uninteresting, because the reason why we found a lot in Trifid and NGC 6352 is that nobody looked very hard in Trifid and NGC 6352. They're terribly nebulous regions. They're far in the southern hemisphere, and there's no major papers by optical astronomers. Whereas if you go to the north and take nicer regions, there's a lot of papers by optical astronomers, and they found them all. So my personal opinion is that we don't have to change the estimated star formation rate of the galaxy, which is all based on OB star counts in the galaxy. That's probably okay. But I don't know that that's the conclusion. We haven't finished this paper. And then, some of you may remember Lisa Townsley visiting you some time ago with early data like this, and she now has an incredible amount of new data like this. And this is just one out of like 20 pictures she has. The blue here is diffuse X-ray emission. All the X-ray stars have been removed from this picture. And in this case, the green is IRAC and MYSTIX. And it's just fantastic. She finds these blue blotches that you sort of look at it and you say, something's wrong in the ACIS detector today. It has background blotches. And then you put on the IRAC map, and they're counter, I don't know what to say, wherever there's an IRAC cloud, there is no X-rays and vice versa. They're anti-correlated spatially. The X-rays fill the interstices between molecular clouds. The X-rays are from shocked OB star winds. It's beautiful. It is the origin of the hot interstellar medium. First, the star has a few million years of having a wind, and that makes this interstellar medium. And then it goes supernova, and it makes some more hot interstellar medium. And people have mostly thought about the supernova, and they forgot about the wind phase. And Klaus Lederer showed that there's as much gas and as much power in this phase as in the supernova phase. So this is very important for the physics of H2 regions, for the origins of the hot interstellar medium. And this is the work of Lisa Townsley and Patrick Bruce. And this is, although you'll find some maps coming out on AstroPH very soon, the interpretation will take her years. It's very, very complex. And if Harvey is in the room and others responsible for Chandra, Chandra was never designed to find low surface brightness splotches on arc-minute scales when there's also 1,000-point sources. You should congratulate yourself for what Chandra can do. This is an accomplishment that was not planned and it's just beautiful. Now let's go back to Michael Kuhn. Since my computer died, I don't know what time it is. How much time do I have?
You're 4 minutes over.
I'm over.
Yes.
Okay. So anyways, I want you to know that mass segregation can now be calculated using some very advanced methods from the Journal of the Royal Statistical Society. And this shows that we can find a mass segregation in even irregular places. This shows that we can do two-point correlation functions taking out the clusters and asking is there any residual clustering. And in some cases we find there is not. In some places we find there is. And someone named Cartwright and Whitworth have another statistic called Q for this purpose. And we have another one that comes from another advanced paper in statistics. And our conclusions are that high-resolution X-rays together with near-infrared and mid-infrared data and some rather fancy statistical gee-whiz methods that hopefully are not reasonably reliable, we can get a large census of young stars even further away than is generally done. And we have an age estimate. We get an empirical view of the star formation history in giant molecular clouds that is emerging. And generally speaking, the dense clusters form at different times in molecular cores. They evacuate the molecular environment. A lot of this is sort of suspected, and they dynamically expand. And we actually have new evidence for this, which has been expected. The subcluster mergers and the filament feeding, I don't think we've proved it. I think they're reasonable interpretations of some of our results, but I don't think it's as definitive yet. A mass aggregation, by the way, is sometimes present. Dr. Alves, not always. Okay, it's been a controversy, and we always see an older generation of dispersed stars in these regions. So I don't know if you know this word, a palimpsest. It's from the medieval times of layers in time, of things and smudges, and you're seeing old things and younger things sort of superposed on each other in these massive regions. So we will continue this work for some years. And work with theorists as well as observers in continuing our studies of massive star formation. Thank you.
All right, we have time for a few questions. Let's start over here.
So, of course, there's another perspective on this from the Herschel data. And they have this catalog of these cold cores seen in the same directions you're looking. Could you tell us what you find to be the relationship of the Herschel cold cores to these clustered ellipses that you derived?
That paper's on the list. We haven't started it yet. So no, I can't tell you. But we absolutely agree with you that Herschel data is oops. I was going to say more valuable than Spitzer data, but I shouldn't say that here. But it's very valuable. Here we go. The Spitzer data tends to see the surfaces of clouds in great detail, and Herschel sees the actual formation of forming clouds. You should know that our samples are not particularly good at class 1 and at class 0. Okay, we don't particularly go to class 0 at all. So what really I think is we should probably add Herschel protostars on top of ours, put them another symbol, a color on them, and then look at them and pick it up together. I don't know the relationship. So, Ben, Alyssa.
I'm just trying to get Mike so I can.
I think it's attached to you.
Yeah.
It's got my anyway, so to defend Spitzer for a minute and defend observers, you seem surprised by this result of finding the young stars in the middle and the old stars on the outside. But there's been a controversy ever since the original Spitzer images of these clusters where some people believe that that's just because, what you said, because the young stars diffuse out over millions of years, and other people believe that there used to be dense gas there and it's not there anymore, which was the sort of theorist picture that you were talking about. But I don't believe that, and so I'm not surprised.
You're not surprised.
Not at all. And so my question to you is, if you do believe the sort of diffusion picture, don't you have enough data to say how long that takes and what the ages are in order to...
We'll work on that. 1 or 2 kilometers per second effective age.
It's not very much.
I think Costa and I in the hallway came up for the larger scale gradients, maybe characteristically of 3 to 5 kilometers per second, but that's a large scale. We don't actually believe there's a wave necessarily traveling, but that's the effective velocity associated with these things. So that's useful. It's something like that.
It's useful and it agrees with the small amount of spectroscopy that's been done.
Thank you.
Yeah.
Your stellar density versus size relation, it seems to me that what that means primarily is that every core has 1,000 stars, right? And that the 1,000 stars occupy a smaller volume at the beginning, and then later they occupy a bigger volume, and so they always fall along this line of density going as size to the -3.
Except for the merging. So we really need a third axis, which we do have, and what we will put on. And this was all in the, anyways, we're going to do this. I think, in fact, that they're generally formed, most of them, as dense, young, and relatively low numbers, as in hundreds, not thousands. And then through the merging process, they vary. Some of the clusters reach up to thousands. Only the big ones that become NGC something. And so the merging has to be put into that story. Otherwise, what you said is right. But I don't think it is right exactly the way you said it.
Is there any other pressing questions?
What was the slope of that density versus size?
I'm not going to say.
It looked like -2 to me.
Yeah.
-3.
Yes, that's right. And that's why I'm not going to say. Okay? Because it's actually interesting to know exactly what that slope is. Okay. And we're still thinking about it. So I'm not going to say.
All right, if there are no more pressing questions, I'd like to thank the speaker one more time.